Good afternoon, everybody. My name is Janeteas, and I am the manager of the Professional Services Group here at Javelin. I hope you've enjoyed our event thus far. We're going to be closing out our time on the main stage on day 2 today with a little look under the hood, pardon the pun, on some of the additive manufacturing applications that we're seeing used in the automotive industry today. We're going to look at some of the different apps as mentioned, and then the technologies and the techniques that really drive them home and make them work well. A little bit more about us in a group. So we're the professional services group within the additive manufacturing division of Javelin. We focus on providing our customers with leading edge solutions consisting of 3D printing hardware, 3D scanning hardware, industry leading software, whether it's metrology oriented or design oriented, as well as our group's knowledge and industry expertise that really drive the application supporting and used by our customers. Now we do this for in-house solutions for our customers as well as through our professional services group. This is a group that I'm managing. We are performing digital and physical solutions for our customers. So in the physical realm, that's everything additive manufacturing, as well as some traditional stuff. Our core competencies really begin, prototyping, advanced prototyping, functional advanced parts, tooling and manufacturing aids, direct digital manufacturing, end use part production, low volume production, as well as all the design for additive manufacturing that really makes these solutions impactful at the customer site. We also do digital solutions as well, so 3D scanning, reverse engineering, design, product development, and again, DFAM, as well as consultation and applications development. So we will work and spend longer periods of time with our customers, whether it's for stuff that we'll be printing or for our customers that have our systems in-house, and really take a deep dive into their organization's need and find areas that we can improve with additive manufacturing. Before we dive into it, we're going to start today with just an overview of some of the principles, some of the technologies, and where we see things being used in the industry, and then we'll dive in a little bit further. To give some context to this presentation, I'm not hoping that it's going to be a complete guide to using AM for automotive applications. 45 minutes is not nearly long enough to dive into that. So what I'm really hoping to do is touch on some of the technologies, the principles, things like that, and help you get thinking a little bit more of like, oh, okay, I see this being used here. I can definitely use that and use this process and technology for this application within my organization. So if there's more questions after this, that's good. I hope that happens. And I would love to connect after this presentation, next week, a couple months down the road, whenever works best for you in order to discuss further. And hopefully we're seeing some ideas come out of this presentation that, makes the light bulb go off for you. I will also mention we're not going to be talking too much about metals in this presentation. Again, 45 minutes. We would need an entirely separate presentation to go over metals. But quickly to summarize, we see it in high performance, low volume applications as well. So we face a lot of challenges in the automotive industry, and although there's unique challenges to each organization, they typically kind of fall within the same wheelhouse. So we're always trying to optimize timelines, productivity, as well as optimize how real our products are looking and optimize the time at which they look real in the design process. So having more realistic parts earlier on in the design process. We also want to optimize our design, making sure we're optimizing things for the manufacturing process and optimize the parts in use, so safety and ergonomics when we're considering a manufacturing environment. We also want to minimize errors and costs. That's pretty standard, but it's still something that drives a lot of the use for additive manufacturing today. We also, of course, want to minimize reworks and retooling. We want to minimize the time to market and really get our products out there faster, and additive manufacturing helps us do that. We also want to streamline things. So we want to streamline our design process and our bridge production processes. We don't want to be overcoming these hurdles or these canyons or these valleys of death once we're finished with our design and getting to the production stages. We want everything to flow on a nice continuum, and ideally being able to use the same tools, parts, CAD designs throughout all of the processes in order to make sure that everything's working as efficiently as possible. We also want to be streamlined in our response to changes. So being able to come up and address a problem or a challenge or a last minute change quickly and efficiently. We also want to make sure that our supply chain is rigorous. So additive manufacturing helps us overcome some of the challenges with respect to overseas production, sustainability, and as well alignment between OEMs and then the different tiers of suppliers. We want to make sure that we're all aligned there. We've had a pretty challenging time during COVID, and I think a lot of us face different challenges around supply chain. So it's something to consider when we're looking at additive manufacturing. All in all, we want to do more for less and faster. And when we're looking at implementing additive manufacturing, we make sure, and our group especially takes a needs-based approach. So we look at what problems is an organization experiencing, or what are the needs of that organization being driven by the problems, and then what are the solutions that could address that, additive manufacturing being one of many. This is a point I really, really like to hammer home. We're not 3D printing for the sake of just 3D printing, just because it's sexy, it's nice. We're 3D printing because it has tangible benefits that are improving our processes when compared to how we would traditionally do things. And when we're using 3D printing, when it's being driven by a need, we see those outcomes that we're looking for. We see additive manufacturing being used throughout the product development lifecycle and throughout the manufacturing lifecycle within the automotive industry. So everything from concept modeling and advanced prototyping to different tools being used in production, as well as end-use parts as well. Things like on-demand production for small batch changes, things like that. And we're going to dive into and look at examples of each of these different things throughout this presentation. Before we do so, I want to kind of give us some alignment with what technologies we're commonly seeing in these different stages. And so on the left, we again have product development, and on the right, more into manufacturing and production. Typically, when it's lower volumes and we're looking at making things look as realistic as possible, simulating injection mold components and fit, function, and aesthetics, that's where we're seeing resin-based systems being used. So our PolyJet technology, multi-material capabilities, true Pantone matching, rubber-like materials. This all makes that product development process faster, easier, better. When we're getting into larger parts, still one-offs, but we need, say, a larger single part, again, single material. That's where we start to see SLA come into play, because you're combining low cost, great surface finish, and accessibility. FDM also, we see that gradient nudging into here. I'm a big fan of using FDM, obviously, for advanced prototypes, but as well as conceptual modeling. When it's just a single material part, a lot of the typical, the FDM parts don't look as nice considerations can be overcome with a clever orientation. So we use FDM throughout those stages as well. And when we start shifting from advanced prototyping into manufacturing, we still are sticking with FDM. So it's robust parts. We're seeing it used for manufacturing aids, jigs and fixtures, 100 part counts, custom manufacturing as well. And then we start to hit a cap, around 50 parts, 100 parts, depending on the part size. It just doesn't make sense anymore. And that's where we see the sintering and fusion technologies and DLP processes coming into play. So these are high throughput, high accuracy, and the material properties are equivalent, if not better, to their injection molded counterparts. I wouldn't say we're at the point now where you should expect to replace all injection molding with 3D printing. And I'm not sure we'll be at that point within the next decade, to be honest. But we're starting to see more and more improvements to the throughput, the material capabilities, and the accuracy of all 3D printing technologies. And this is enabling use in a more diverse subset of applications. We're going to talk a little bit now about some of the principles and enablers that allow additive manufacturing to make such an impact. The first one is design freedom, and we hear it a lot. The only limit to what you can print is what you can think to design, and then, of course, the mechanical limitations of the printer. And that truly is the case. So when we adopt additive manufacturing, we are focusing and designing for function. We are optimizing outcomes and functionality. We're not worried about manufacturability. So we're not saying, oh, it would be very nice to do this and this would make the tool better, but how would we see that? We don't have any of those limitations. So we can really go down the rabbit hole as far as we want in terms of optimizing our designs, whether it's a prototype, advanced prototype, or our tooling, manufacturing, jigs and fixtures. That's commonly where we see the most complex and unlimited designs with respect to freedom. We're also moving in the direction of higher fidelity for our prints. So we see with the PolyJet J series, true Pantone colors, working directly with rendering softwares. This kind of realism really allows us to make informed decisions in the design process and earlier on in the design process. So we're not faced with concerns about whether our prototype is reflecting the actual product, because it is reflecting the actual product. High fidelity also accounts for our material performance, and we kind of get into this high performance bubble as well. So high performance of the materials we're printing, as well as high performance of the printers themselves. So again, looking at high performance materials, we're able to start replacing parts that are traditionally made out of metals with our high performance thermoplastics. We're also seeing good performance of our resin-based systems where they're able to do true Pantone colors and give some of the functionality of an injection molded counterpart part. And with that being said, we can have one part that's looking at the design, the fit, feel, finish, as well as the performance and functionally testing the part. High performance for the systems as well. So we are doing large parts with great levels of accuracy really quickly. And when you're implementing additive manufacturing in a production environment, that is key. You need to rely on these things to run 24/7, lights out, and not have any issues, and spit out the parts that are accurate and work. And we're seeing that more and more, especially with our Stratasys FDM systems. I mean, they've been a backbone of FDM for a long time, and we're still seeing that reliability and that throughput, even as we come to more and more exotic materials. So we're not losing all the benefits as we start, say, printing a large nylon 12 carbon fiber part. We're still seeing that same base level of performance that really you need to rely on if you're going to be bringing this into your production setting. And then finally, digital processing. So this is really that ecosystem that we're preparing and printing our parts in. It's coming together. We don't have to design, export as STL, import into Insight, slice it, set all the parameters, do all of that. You can click a button, go straight CAD to print. You can import your CAD assemblies, print it as one piece, and apply different material properties. You can import your CAD assembly, break it all apart, and just print it separately, but not have to do that in the software, not have to save out individual bodies in the software. We're also seeing connectivity with rendering softwares and different things like that. That's making it much easier for the design teams to print their parts and have hands-on review within a 24-hour cycle. And that's something that's really improving our time to market. Before we start looking at some of the product development applications, I just wanted to put some examples. We'll revisit this part a little bit later on in my presentation. But when we talk about design freedom, this is a part that's been designed specifically for additive manufacturing. We can see all of the integrated features, integrated hanging tools, integrating mounts, integrated pneumatic lines. But we've also seen where we've been clever and ensured that we're implementing off-the-shelf parts so that we can replace and repair this thing easily. We're also implementing ergonomic features, lightweighting the part, things like that. And that ties into our digital processing as well. So this is an interior view of that same part. The magenta portion is actually the internal pneumatic channel. And then with this part, by importing the CAD directly straight, in this case, we went straight from SolidWorks to GrabCAD Print, we're able to optimize it further, reduce print time, reduce material consumption without having to go back into the design stages. One of my favorite tips and tricks is multi-body infill. So bring a part, bring an assembly in, and then assigning different material properties based on what the required strength is. So if you have an interior strengthening rib, print that solid, but the housing of everything can be printed in a sparse. For example, in the handles here, we do them sparse, but we have a solid body to provide strength for the jig. We can also selectively reinforce and select features in the CAD. So holes, faces, bodies can also be selected and selectively adjusted, reinforced, seam avoidance, etc. The final thing and really powerful thing that we see quickly is just very, very quickly adjusting holes and different features. So in this particular part, it sees that there's a round hole there. We've taken it and can tell it to be self-supporting right away. And with that, we've gone through a bit of an overview. We'll be going back to some of these different principles as we go throughout the presentation. We're going to look at product development now, concept modeling, and advanced prototyping. With concept models, really, we're using them to test fit, aesthetics, form, make design changes, look at colors, things like that. Implementing additive manufacturing lets us design iteratively, early and often. Much easier to communicate your ideas when you have a part in hand. Something as simple as scaling is really hard to get a sense of until you're printing and feeling that part. What enables us to be and have a lot of wins in the concept modeling space is the excellent tolerance, material options, and resolution that 3D printing can afford. And then similarly with advanced prototyping, fit, assembly, test, and I'm talking test in the real world environments with the real materials that you're going to be using in production. So this gives you an unparalleled window into how the part's going to perform when it's finally in production. Also, we're going to be eliminating and reducing the scraps and rework and things like that because our prototypes are performing true to the production part. The enablers here, again, the materials, high accuracy, high performance. We have, flame resistant materials, things like that, that are really letting us prototype in advanced applications. the thermoplastic stability, and the reliability of the systems all come into play here. Let's take a look at the first part in the presentation. This is done on a polyjet system. Any of the J series can accommodate this. This one was done on the J850. This is a concept model of an Audi tail light, early stage concept, probably from the A series. So when we did this part, this is printed in one piece. So all these different colors, that's assigned in the print prep stage. It's not assigned in SolidWorks or any design software. So what we're doing is we import the CAD. Each different color is a different body. We're telling the printer what color we want what body to be and assigning that. Final thing is to orient the part. In this particular case, we would orient it with the outer surface or the A surface down because that's the easiest to polish. This one would be an overnight print, 8 hours or less. And then coming in, quickly take the part off. It's ready to have a look at. If this was being used in a marketing event or needed to be exactly like the real life production version, it would just be a quick wet sand and clear coat on the downward facing surface to get rid of some of those occlusions there. When Audi's doing this, they have some J series printers from us. They see on average a 50% reduction in the time to market for a given product. They're a company that likes to prototype everything early and often. So bringing this whole process in-house will really allow them to expedite their design process and not be reliant on, a third-party service bureau or traditional techniques to make these parts. It also helps improve communication and ultimately leads to a better production part. Similarly, we're going to look at an AP Racing brake caliper here. So again, they have a J series, a J750 from us. This is an FEA exported directly from SolidWorks, or any other design software can do this as well. Again, several different caliper designs or component designs can be done in one print, lights out production here. In this particular case, the customer really likes the ability to print the thermal graphs over top of the parts to help communicate with their customers why they're making design decisions and how those design decisions impact performance. On the brake rotor here, you can clearly see the areas of thermal stress. And so if they've made a different design or a change to accommodate that and improve that, it's very, very easy to showcase this with a physical part. That also then lets you test up and bolt up all the hardware, mount it up to the brake assembly and really test and make sure that the design is going to work. This one again, J series would be a standard VRML export or FreeMF export from your design software, printed, let the printer decide on fastest orientation, matte surface finish, done. Overnight, hands out, maybe 30 minutes of operator time, 8 hours of print time, and you're left with a beautiful part. Moving more into the advanced prototypes side of things. So this is an air intake manifold for the 1.8 turbo Volkswagen engine. SCM Motorsports is a customer of ours that we've been working with for a long time. This air intake manifold was printed with FDM, lets us do a large format print with high accuracy. We selected Ultim 9085 for this print for a number of different reasons. And then we optimized the design a little bit. Of course, there's going to be a cast part, so we didn't go too crazy with the design optimization for the part itself, but we really optimized how we printed this thing to give us the best results when we're talking about accuracy and functional testing. On a part like this, I often recommend that we're moving, we'll do an ABS for test fit and then get into structural testing and advanced functional testing with a higher performance plastic. But the customer was quite certain of the design here, and we knew that we were pretty much there. So we went straight for an Ultim print. We used this, obviously, as you can see, we installed all the hardware on it. We checked it out. Then we bolted it up to the car and we ran it on the dyno to make sure that we were seeing what we thought we would see in the simulations on a real world test. We weren't satisfied with that. So we took the car off the dyno and drove it around Toronto for a couple of days. True real world performance testing, because most of the customers will be using this product in day-to-day driving. And we really want to make sure that we're getting the performance that we'd like. And we're able to do that very, very early on in the design process with a high performance thermoplastic prototype. This part was also used as a surrogate for post-machining to kind of figure out the CNC programming and the different processes there as well, and used as a surrogate for the packaging and dummy trays and things like that once we're working with the metal parts. Another advanced prototype, a simple body panel, but the timeline in which this was done is really quick. So this was a last minute late change, design change to the area around the exhaust port. We were able to print a part like this in 3 pieces on the Fortis 900. This particular material is a polycarbonate. It allows us to hot air weld it or solvent weld it so we can work with it very, very easily. It's functional, right? We have both the A side and the B side here. So not only we're looking at the design changes to the outward facing surface, we're also able to implement all of the mounting surfaces and truly mount it up on the car versus being stuck with the fiberglass prototype where we're only looking at the A surface. This part was CAD to on the car in 3 days, which is a substantial improvement over how this would traditionally be done. And again, we can use this for functional testing, design verification, and the same part can also be used as a surrogate to help design different assemblies, different jigs, fixtures, packaging that are going to be used in the production process as well. And we're starting to see some fusion. Of course, that's not a comprehensive list of all of the different things, but the principles are there. We're seeing concept models being afforded by high realism, true to color texture, high performance, and advanced prototyping as well. We're seeing the materials that last, they're strong, they're durable, and enable us to mimic the real world environments. And in most cases, the actual material we're going to be producing with as well, and truly validate what we're doing. I started mentioning some surrogate parts there, and there's a little bit of leak into manufacturing and production. And that really is because it is a continuum. There isn't a strict stop for one technology and a strict start for another technology. So my first slide going into manufacturing and production will eventually be, again, on surrogate parts. But first, just to recenter ourselves, we're back in the manufacturing and production. We've looked at product development. And now let's take a look at some application examples for manufacturing aids, tooling and fabrication, as well as end use parts. So with manufacturing aids, we see them used all over the shop floor, whether it's in production, assembly, logistics and transportation, and QC and inspection. And again, don't take this as a comprehensive list. These are just some of the most common use cases, but really focus here on the principles of what we're doing, what we're seeing, and how that could be applied to your organization. Within production, commonly, masking aids and trim tools, drill and riveting guides, end of arm tooling, teaching parts, surrogate parts, just to name a few. Assembly, a ton of jigs and fixtures, assembly aids, guides, again, surrogates, non-marring parts, more end of arm tooling as well. For logistics and transportation, a big one is using our 3D printed surrogates to design all the packaging for different automotive applications, as well as creating the actual dunnage trays and things like that with additive manufacturing. We're doing a lot of end effectors for this space as well, and then doing custom packaging. And finally, within QC and inspection, CMM fixtures, conformal tooling, go-no-go gauges, measurement aids, things like that that are really helping us ensure that the production parts are to spec as well. And with that, let's look at the first application in this section of the presentation. That's, again, going to be surrogate parts. So we can use, two designs, if you will, for a number of different functions around the shop. So we can use the model and print the model as cast, as well as print the model as CNC. And I always encourage our customers to do both because there's a number of applications that you can use. And with the cast model, we can program the robotics, we can prove out our CNC programs. We can actually go as far as performing the operations on the printed parts as well. So it's not just, ghost moving around the part, but actually going ahead and, milling the part if we want to do that. We can optimize these parts so that any areas that are going to be post-machined can be solid and everything else is sparse. That way we're optimizing our material consumption as well as being able to use the parts for testing functions. And then with the as machined model, we can use it for assembly testing, training, assembly line checks, things like that. So there's a number of different use cases for one surrogate part, if you will, throughout the manufacturing process. Commonly, we see FDM being used for these. Large format, high accuracy with a diverse material selection. So, if we're making a polycarbonate part, we can print a polycarbonate part and machine it and see what the outcomes are going to be. And I mentioned already, we have unlimited control of the part interior. So that really helps us optimize both the function as well as the cost of these models. This is an exhaust welding jig. I've chosen an FSAE example because we have unlimited access to all the different things and pictures and parts, but we have a number of customers in automotive and in transportation, forestry, using our parts for this kind of application. So this is quite simple, honestly. It's just an ABS print, mostly sparse. We may selectively reinforce a few areas. Total print time on this project was 24 hours. So, the team got their designs to us a little late. They were in a rush. And, hey, we really need to start welding these on Monday. Threw them on the printer over the weekend, pulled them off Monday morning. They were welding by the end of the day. They were able to go ahead and weld their first exhaust without any issues, any adjustments, bolted right up. So It's a quite straightforward application, but something I really like to highlight. Not every great application has to be the most complex application in the world. Sometimes the simplest ones, we're still seeing great outcomes and great effects there. Next, we're going to look at an assembly and a QC fixture. This is from a customer of ours, Solaxis. They have about 9 or 10, I think, now of our Fortis 900 systems. And again, they provide custom assembly aids, jigs and fixtures and things like that for both the aerospace and automotive industry. And they have really implemented additive manufacturing for a number of different applications. I had trouble choosing which example of theirs to include, but I really, really love this because it just highlights a number of the things I've talked about earlier. We're seeing a large part, we printed this with FDM, this is a Fortis 900 build, lots of consolidated features, but again, a balance of consolidation with off-the-shelf standard parts for easy repairs. What we can see on the interior here is that we've optimized the interior fill for this jig as well. And we've also integrated some QC functions. So this is an assembly jig for a door seal. So it both holds the door in place to pop the seal on, as well as QCs to make sure that we have everything within spec. By switching to additive manufacturing, we saw a 75% time reduction per design cycle. So this is a jig that's been iteratively worked on and has been in circulation for 5 years now. I think they've done about 5 or 6 cycle changes. And every time they're doing that, it's 75% less time than what it would take traditionally. The jig itself is 100 pounds lighter than what would traditionally be used, or the old one it's replacing, which was CNC'd out of aluminum. And so we're really seeing a substantial improvement. You can take this jig, I could physically pick it up, move it everywhere. The biggest impact here, aside from the direct impacts, is cycle times. We've reduced cycle times and we've reduced compliance issues by integrating QC in here. So, if we're taking 10, 20, 30 seconds off a cycle, or we're doing hundreds of cycles per year, it's very quick to see how, or very quick and easy to see the benefits of implementing something like this down the road. So if we're able to see those benefits and also make gains by using additive manufacturing for the jig itself, there's a twofold win, and that's something that I think is really important to consider when we're looking at implementing new tooling. This is just another picture of the jig in use, so you can see the green go light in this case. The seal's been installed correctly. Again, I should point out that this too, enabling and moving to additive manufacturing for this also enables having a digital inventory. So if there was ever an instance, and I don't think one of these is actually broken, but if there was ever an instance where one broke, it's very quick, easy to print this. This would probably be a weekend, assuming it's printed in one piece, would be a weekend build. So very quick and easy to replace the parts, optimize them, update them, or deploy more if we're starting to see more and more be deployed. This is another really good one. This is one that my team did start to finish. Our old office was right next to the GM plant in Oshawa, and they came over one day and said, "Hey, we're taking on some pickup truck manufacturing from while they retool a US plant, and we need a new fixture. The guys are using a lift-assisted metal fixture to put on some door emblems. We have a couple different models. We need one tool to work with all of the different models, and we need the parts. We need the trucks being put off the assembly line within 2 weeks." We got all of the Class A surfaces from GM, and within a week had our first prototype printed. Over that weekend, did the final production parts, and they were ready to go. This one, again, FDM, and I think we're seeing a common trend here that as we're moving to the lower volume, high performance parts, FDM is a clear winner here. So what enabled us to do this was obviously the performance and the accuracy of the systems. We consolidated some features and leveraged the optimized internal structures. You can see there's a lot of off-the-shelf parts there as well. We wanted to do that so that people could locally source replacements if needed, or looking forward, if this is implemented at different plants, different areas, different manufacturing facilities, that they can easily get access to the same hardware we need. We also did, if you look at the CAD picture there, an insert-based approach. So each truck or each model just has a different insert for that badge. Quickly swap the insert and continue printing. If we're looking at what the design time and production cost of this piece would have been with traditional manufacturing, we had the parts in production before we had this jig and fixture in production before their first initial prototype would have even been completed. So substantial savings here. Again, we're replacing lift assisted fixtures. So the shop guys loved it. They were raving on and on about it. We did a few more for them, and it was so effective, and the cycle times were reduced so much that they actually decided to take this approach for all of the badge fixturing across North America for their truck lines. So this was a very quick, I shouldn't say easy, this was commonplace for our team, but something that we were very quickly able to turn around and support a customer with doing. End of arm tooling is another area that we're seeing substantial benefits with additive manufacturing. This is a particular one that we've probably seen, and any of those of you who've seen our presentations before will have seen this end of arm tool. It's a really nice example because, again, it exemplifies integrating different features, feature consolidation, designed for additive manufacturing. Pardon me. Typically with end of arm tools, we're seeing Ultim 9085, nylon 12 carbon, ABS carbon, and then our simple ones, ABS, polycarbonate, PC ABS. A lot of the different design for additive techniques are typically leveraging these. Most commonly, it's pneumatic integration of the pneumatic airline, so you don't have external lines. Obviously, there's a lot of safety benefits there. We consolidate components and make everything self-supporting. So this part actually we would print kind of opposite to how it's pictured here, and it prints entirely self-supporting. There's no support on the inside of the part. So you can literally take this part off the printer, let it cool, install all the accessories, and pop it onto the assembly line. We see significant cost and time savings with end of arm tooling. And what we're seeing is faster cycle times because the materials are strong as the aluminum that we typically use, but also lighter. So we can optimize our design so that the robots can move faster, or we can use smaller robotics for a given application. So a number of different benefits that are realized by moving to additive manufacturing over a traditional end of arm tool. For this particular one, we saw 17-day savings and a 91% weight reduction in this end of arm tool. And so you can imagine, knowing the impacts on size of the robot and movement speed of the robot, those kind of cycle time gains that we can see and the resulting economic impacts downstream. Those of you with a keen eye will recognize that this is the printed version of the part from my introductory section where we're talking about design consolidation and digital processing. So this is a quarter panel glass alignment fixture that GM did. This was the final assembly. We ended up going with external lines just for ease of repairability for some sections. You can see some of the ancillary hardware that's been installed. Previously, this part was aluminum with Delrin touching points. I'll have a picture of that coming up shortly. We saw a huge savings, 50% savings in cost versus the traditional weldment that they were using. And this was a 30-hour build. So again, you time it really right, you can start it one morning and have it every day the next day. 4 to 6 weeks was their typical lead time on these normally. We added and implemented, as mentioned earlier, ergonomic features. The handles are much more ergonomically friendly, and other different features that made this thing easier to use. And the total cost was only $1,200 all in, start to finish. We used heat stake inserts for the main suction cup, but the rest of the components on here, this was actually self-tapped. So you don't even have to worry about ordering extra hardware or anything like that. Literally take this part off the printer, tap it, screw your hardware in. This particular print looks to me, this isn't one that we did in-house here, but it's an ABS part, would probably be a standard slice height, 10 thou, and likely here, based on that material cost, I'm going to say this one was built full solid. We're still seeing tons of weight savings as compared to the aluminum tool, but that full solid just gives us the most strength that we can for this given print, which, why not if it's not going to add too much cost. And so we have here pictured the legacy part. You can see what it looked like. It's very obviously bulkier, not as clean, not as nice. And you can see the level of air channels that are in that. So we've still been able to consolidate and improve some things here. Just to granularly point out everything that was done on this part, we reused the current locator details, mounting brackets, and pneumatic controls from the existing, so we didn't have to redesign that system. But we integrated the quarter glass suction cup grip. We integrated the gauge protective deflector, as well as the integrated pneumatics for most sections. We also added trigger style suction on-off switches, integrated eyelets for stowage, and the handles are also integrated versus being an accessory. So Reducing the number of parts we need to order, all that kind of stuff really helps us get this part on the shop floor and performing as soon as possible. And we're seeing it perform, no difference to the aluminum tool with a ton of savings. I'm going to go through a couple more just kind of rapid fire examples. So this is a non-marring badge placement fixture, badge placement, pretty standard. We're accomplishing this by printing with our FDM TPU 92. It's a short 92A material available in the F-series systems. Again, works with soluble support, so we're not giving up any complexity. A part like this, they printed at Lang flat, would be a 3 or 4 hour print, 2 hours to dissolve in the tank. And so you could have this either, first thing in the morning from an overnight print, or have it on the shop floor within the same day. And this is actually from Victory Motorcycles, Polaris. They're doing a ton of non-marring fixtures for all of their different assembly lines out of this TPU material. Conformal tooling is another one. This is in particular a machining fixture. This is done out of our polycarbonate material. This part itself is also a 3D printed part. So we would have done some DFAM on here, as well as use that part to design the tooling. Typically, anything printed with the MLS is as cast. So we're going to obviously need to machine that to a nicer surface finish. And we need a custom machine to do so, or a custom jig to do so. So we'll leverage 3D printing. This one is just just a standard PC block solid. We could integrate cooling lines and things like that if the application calls for it. This is an assembly and a QC check jig. So this entire structure is 3D printed, Fortis 900 ABS material. It's going to be a standard 10,000 slice height. The reason that works so well is because of our soluble supports. You can just put it in the soluble solution, pull the parts out, and have parts that are ready to go with no operator time. This was also then nickel plated to give us the more realistic performance and feel, a little bit better wear resistance as we're mounting and unmounting a number of different panels to this piece. And so what this was really used for is to QC and check all of the internal panels that were being produced for this vehicle, and quality check our customer supplier to make sure that all of the parts that they're producing in the production are within spec. Very quick, simple. You can see this is on a rolling thing, so very easy to quickly roll around and check the different lots that are coming in from the different customers. So with that, again, not a comprehensive look at all the jig and fixture applications, but certainly a very good look. We're going to hop and look in some tooling and fabrication examples now. Most common areas for this: forming, composites, and prototype molding. In this area, for say customers that are doing lower volumes of vehicles or heavy equipment or more custom things, upfitting, things like that, we're seeing these technologies being used in production. And as well, forming, that's pretty commonly replaced traditional materials as well. When we're looking at higher volumes, the bigger OEMs, things like that, we're probably still sticking with traditional methods for the actual production, but we use a lot of these techniques in the prototyping and development space. So I wanted to talk about that within the context of how we use this for manufacturing. So first and foremost, forming, sheet metal forming. This was a PC block, 22 hours CAD production part. We're cutting and pressing a mild steel, 2400 PSI. You can see the process in which we took the shaped steel, mounted it up, pressed it, as well as drew the trim lines on this. So another common technique that we do here is using a 3D printed part to mark out trim lines quite easily. And often actually we're 3D printing the trim tools as well. So you pop the trim tool on there, do your work, and it's done. Nice and easy. Very easy to visualize how we're going to trim, where we're going to trim, and what the part's going to look like when it's finished. And we see this again, the sheet metal forming, hydroforming. Commonly we're using PC, sometimes ABS. Now we're getting into applications where we're using our nylon 12CF or our Ultim, and really moving into those production settings. This particular part was solid. Again, I'm always the kind of person that likes to be on the safe side and have it be more robust for the first pass and then optimize as we go. But we can optimize the interior fill on this part if we need to. Another common application is thermal forming. Now, again, in an OEM production setting, we're not going to be using this for necessarily production. There's not necessarily a lot of thermoformed parts in a production vehicle, but when we're looking at heavy equipment, custom machinery, again, upscaling, upfitting vehicles, this is a really common application. This particular part, we used to thermoform 40 thou Kydex. It's an Ultim 9085 piece. The really unique aspect of this part is that it's actually, if we were to see the underside of it, it's completely hollow. There's no backfill there. And the other really cool thing about this part is there's no post drill holes. So we haven't gone through and had to drill in any or any holes for air suction in this post print. It's all integrated with our print setup. This also printed without any supports. You know, in that cavity in the back, we chose self-supporting angles at the top. So we're printing this with no supports. Literally can pop it off the printer, put it on the thermoformer, and away we go. We can optimize and use the same tool for different, or same tool design for different plastics that we're thermoforming, simply by adjusting the airflow and the gap between adjacent tool paths within the print. So one CAD design, you just adjust the print parameters and you can be pulling, 5 thou thick Lexan or 40 thou thick Kydex. This particular part was used for low volume production. I think the part count was just below 100 or something like that. Traditional tooling here would have been cost prohibitive. Obviously, additive makes things a little bit easier. When we're looking at composites, again, for high-end motorsports applications, fitting vehicles, accessories, we're using additive manufacturing to produce composites in a production setting. When we're looking at product development and production is, parts in the thousands or the hundreds of thousands, we're not going to be seeing soluble tooling or even traditionally made tooling being used. One challenge, and it's, I don't want to go through this presentation and not address any challenges that we see with AM. One challenge with using thermoplastics for tooling, whether that's soluble or traditional, is that they have a pretty high CTE compared to metals. And so we're still kind of chasing that white whale in terms of a low CTE 3D printable material. We're pretty close with our Ultim 1010. A lot of people like to use that for kind of open back processes. We can really optimize the mold, shell it out on the back. So from a prototyping perspective, you can have a really, really cost effective but high performance layup tool that you can then use to make your prototype. These particular examples are actually production parts for Championship Motorsports. It's an aftermarket Porsche upfitter. So it's going to be a production setting because the volumes are quite low. This particular part, you've got the soluble tool and then a clamshell that they use while the epoxy resin is setting, or the resin setting, pardon me, and then it's taken off. We have a really nice surface finish on both the inside and the outside of the part. The soluble tool allows for a seamless part. So this tube is completely seamless. And when we're looking at high-end aftermarket car parts, that's particularly important. I think one thing that I see coming into play is really using this to test out and evaluate and prototype composites that are leveraging organic fibers and looking towards integrating sustainability into the composites world. So again, when we're looking at production volumes, not quite there yet, but when we're testing out different organic fibers and composites, using our additively manufactured tools allows you to do so for a much more cost-effective, or with a much lower cost. Moving beyond those kind of fabrication tools, we're going to look at end-use parts very quickly here. We've got custom manufacturing and low volume production. Again, this is the part counts in the tens and in the hundreds. This is an end-use suspension arm for a solar-powered vehicle. Nylon 12 carbon fiber, 10 thou. We printed this on the 450. We went interior fill solid because we wanted this part to last in the competition environment. Likely we could have gotten away with printing it sparse or double dense and still seen some performance improvements. We saw lighter, the part was lighter, and we saw a significant reduction time versus how they would typically produce this part. Sorry, that should say 10 pounds lighter, not 100 pounds lighter. Added an extra zero in there. We also, again, saw cycle times with their prototyping and product development stage, and this was also a student team, so we decreased their compliance issues by 3D printing all their prototypes for them. And the final application example that we're going to have a look at, this is an end-use part that's being used in the IndyCar series this year. Any of you who follow motorsports know that with open wheel racing, we're moving towards keeping the drivers safe, either with the halo or with the windscreen. With IndyCar implementing the windscreen, what we noticed is the drivers were having much hotter environments when they're driving. And if any of you have driven a race car, you know it's a hot place to be already. And so what Stratasys did, they worked with the IndyCar series to design up and fabricate some custom air inlets that are feeding air directly into, as we can see on the photos, the driver's helmet. So in this case, they produced 100 to 150 parts. Advanced print prep processes such as using multi-slice height, adjusting the orientation to give us optimal surface finish and reduce supports really helps make additive manufacturing the ideal production technology for this. We saw a 70% cost savings over how we would do this traditionally. I don't think the tooling actually was even designed up because we knew straightforward that 3D printing was going to be the way to go for this. And with that, we come to the end of our presentation. So again, I hope you enjoyed these last 2 days. We thank you for your time. To get in touch with me, please email us print@javelin-tech.com, or you can find us on our website and submit an inquiry through there. I would love to hear from our audience and chat further about 3D printing applications in the automotive field. Thank you for your time. Bye.